Hi, my name is Tomer, and in this talk, I'll present the application of ensembles to decoding, and I'll refer specifically to a data-driven framework. Now, I have a main goal in mind for this presentation, and that's to stress how important it is to know your domain and know your data when applying machine learning algorithms to practical problems, and specifically to problems in communication. This is the agenda for this talk. First, I'll present a brief decoding background. Then we'll discuss on the importance of data, specifically to decoding. Afterwards, the framework will be presented, and I'll conclude with a short summary. So let's begin. So first, what are error correction codes? They are simply means to increase the reliability of transmission over a noisy channel. We'll work under several simplifying assumptions that the channel is the white noise channel and the codes are binary and linear. And now, assuming you have a message word U of length k that you wish to transmit, the first step is to encode it by multiplying it with a generator matrix G with rows from the basis for the linear code, and then you get some code word C. This is also depicted in this simplified communication system where this C enters the BPSK modulator, and this component maps the 0 bits of C into ones and the ones of C into -1. And then this X vector here is transmitted, and at the receiver, we have the noisy word Y. But we did not decode this vector directly, but rather multiply it by this scalar here and get the log likelihood ratios word, or LLR's word in short. Now, after decoding these LLR words using the decoder represented by function f, we have the estimated code word on the right. And the optimization problem that we'd like to solve is to find the code word that maximizes the a posteriori probability of the code word given the channel observation. Now, before I present one realization of this decoder function, let us first look at a basic property of a linear code, and that's the parity check matrix of the code. This H matrix defines several constraints that must hold for every code word in the code book. So for example here, the first row reads that the summation of the first, second, fourth, and fifth bits in every valid code word must be 0. Now we can also depict this H matrix graphically using the Tanner graph. The Tanner graph is a bipartite graph where the variable nodes are on the left and the check nodes are on the right, and a check node is connected to a variable node if and only if the corresponding element in the H matrix is a 1. Next, the belief propagation is a decoding algorithm that works over the Tanner graph. We first initialize this algorithm with the LLR values from the channel on the left. Then we transmit messages over the edges of this graph and perform some aggregation at the check nodes on the right. Then we transmit back refined messages, and another aggregation follows. Now this whole process repeats for a predefined number of iterations or until we satisfy another stopping criterion. To transform the LLR values back to bits, we'll use the hard decision rule that is specified here. Now observe that the BP is suboptimal in a sense, because it works over a graph with cycles and not a tree, meaning that after a few iterations, the messages become heavily correlated, and this hinders the convergence of this algorithm. We'd like to reduce this correlation, and one approach we could take here is a deep learning one. So under the weighted belief propagation scheme, we'll start by assigning weights over the edges of the Tanner graph. We'll choose appropriate loss, and then we'll optimize this architecture. This assignment actually unfolds the BP into a neural network where each hidden layer corresponds to the messages, and the first and last layer correspond to the variable nodes. We'll work with the binary cross-entropy loss in order to minimize the Kullback-Leibler divergence between the distribution of the code words and the distribution of the decoded code words and the weighted BP output. We'll also sum over all the losses of all the different iterations, and that's to prevent vanishing gradients issues and to help convergence. Also, employing our domain knowledge, we know that the BP only tries to correct the error pattern that is added to the code word, and its decision regions are equivalent around every code word. This means that we can use the inherited symmetry of the problem and train the network using only the zero code word. We've seen the weighted BP model so far, and let's talk a bit more about model and data selections. So first, about the model. Two main approaches exist in current decoding literature. The first is a domain-oriented one. According to it, we'll assign learnable parameters on some classical decoder and then train it, and the weighted BP is an example of this approach. The main advantage here is that we utilize domain knowledge using a decoder that we know that fits the problem at hand, and we only refine it to the specific training data from the channel. On the other hand, we could replace this classical decoder or weighted decoder with a neural network. Now we can use any state-of-the-art architecture that we'd like, and indeed have less limitations on the solution space. The network is able to represent a vast amount of function, contrary to the weighted BP. The downside here is that we have to learn each and every one of these decision regions, contrary to the model-based approach, where we had them a priori. So to recap, the curse of dimensionality is the main factor for the dominance of the model-based approach, at least for now. But we know that in data science and machine learning, the model is only one part of the entire pipeline. Another no less important part is the data. We know that if your data is poor, then the model will perform poorly, no matter what. And while in other domains, for example, in computer vision, the data can be easily visualized. And in communication, we deal with binary or LLR highly dimensional vectors. So it is much harder to make sense of it. Nonetheless, data in decoding also holds a few promises. So while in classical machine learning, we have a small number of samples and the distribution is usually unknown, in machine learning-based decoding, the distribution is specified by the channel, meaning we control the distribution, and we can simulate as many samples as we want. And we'd like to take leverage of these two advantages. After discussing the model and data aspects in decoding, let me present how ensembles are best used in decoding, considering scenarios with limited resources. We'll also take into account the discussion regarding the data and the model, so keep it in mind. We've seen that the weighted BP is rather limited in its solution space compared to the model-free approach. But what if we use a combination of such models? Then we could still utilize domain knowledge while reducing some limitations. To further present motivations for this ensemble scheme, let's first consider the list decoding scheme. Under the list decoding, we take the received channel word and decode it using multiple calls to different BPs. Each branch here sees some variation of this initial vector. For example, this paper performs a different permutation on each branch. Then we take only the valid decoded words and choose the one that minimizes some criterion as the output. But as the authors of this paper indicate, there exists no clear evidence on which permutation is best for a given input. But what if we could have some rule that uniquely maps the received word to the most fitting branch? Then we could save the complexity of the multiple BP calls. So we'd like to have some mapping rule. Let's call it a gating function that uniquely maps each received word to the most fitting decoder. The gating function will have negligible complexity compared to a single BP, and we'd like to keep the same decoding performance of the entire ensemble, using only the gating plus a single BP call. This leads us to the scheme of the data-driven ensemble. Under this scheme, we take the LLR values from the channel and map them using the gating rule to the most fitting decoder, and then simply output the decoded word. We'll also employ the all decoders baseline, where we ignore this gating here and perform the decoding with all the decoders. Score each decoded word, and then choose the one that maximizes this score. This is similar to the list decoding criterion. But now, instead of having a different permutation over each branch, we'll have different weighted BPs. Specifically, we'll partition the input distribution of feasible LLR words into multiple regions. Then each decoder will be assigned with a different region and will be specialized to actually decode words from that subspace. Then the gating function will simply map each incoming word to the most likely region, and then to the specialized decoder. Both the choices of the input partition and the gating function will be domain-oriented. And let me start explaining the data partition part. So for each channel word, we'll use the hard decision received word and XOR it with the ground truth code word. This is done in the training phase, so we do have this code word. Then we get the binary error pattern which indicates the bit flips that occurred in the transmission. Then we'll assign the error pattern to a region, where we would have different regions for different numbers of errored bits. After doing so, we'll append the original LLR word to a dataset, and after gathering enough samples, we'll train all the decoders on the corresponding datasets. Then what we'll have as a result is we'll have specialized experts. Each expert is specialized in decoding words with different number of errored bits. This is one partition based on the Hamming distance, but another one we employed in the paper is based on the syndrome, but I won't have time to cover it. Now, in evaluation, we'll need a gating that approximates the number of errored bits in an incoming noisy word. For that, we'll employ a classical hard decision decoder. See that we could use a neural network to do so, but this would follow the model-free approach, which we know that fails, especially as the dimension scales up. So this decoder works on the hard rather than the soft values, meaning lesser performance, but it also has negligible complexity compared to the BP. It outputs this approximated code word, and again, with SOR, we get the approximated error pattern. Now, by counting the number of errored bits, we can map the word to the most fitting decoder. We refer to this method as the single choice gating. We also employ the all decoders gating as a lower bound on the error rate, but additionally, we'll employ the random gating, which assigns a decoder randomly. And this is an upper bound on the error rate. In the all decoders case, we use this scoring function, which penalizes pseudocode words. Now let's see some results. We can see the BP in yellow and a weighted BP improvement called an active D-learning over here. And even on this improvement, we have another 0.3 to 1.2 dB infer by using the single choice approach. You can see that it also sticks to the all decoders gating, meaning that we have achieved our goals, reducing the complexity of the list decoding while keeping the same decoding performance. We have used 3 decoders and 5 iterations of weighted BPs in this setup. Here you may observe some more results on a different high-density code. Okay, now let's conclude the talk. To sum up, we have seen why knowing the domain is vital to both model and data choices, and especially to successful integration of machine learning concepts into decoding.